So today we're going to run through the E1 mechanism. And so we'll look at one reaction, we'll go through the steps. You can fill out your sheets for the questions that you see. Please fill in your ID and bubble in the numbers. So E2 and E1 are not as, we're not going to go as much in depth with those. So we'll get through the E1 pretty quick, and then we're going to move on to addition reactions. Since elimination forms an alkene, then we're going to learn the reactions of alkenes with electrophiles. And that's where we add two elements across the double bond through an addition reaction. And the addition reactions have a lot of factors in considering them. So I think there's 12 or 15 of those reactions that we'll cover in the remaining time for this module, and then we'll do some alkyne stuff the very last lecture of the course. So unimolecular elimination, again, the one means the rate is only dependent upon the substrate with the leaving group. So typically with these type of reactions, we're using either an alcohol or an alkyl halide with some solvent and then usually heat. So these conditions, even though we're just showing elimination products, can show some sort of substitution as well. So what you'll notice in the E1 mechanism is that the conditions are neutral, so there's not the presence of one of these alkoxide bases or amine bases present. So we're going to look at this example, go through the mechanistic considerations, and see how this intermediate that forms can lead to these different products that you see. So our starting material is this alcohol. And if we classify that, it's a secondary alcohol. The numbering that you see is the numbering for the name, for the IUPAC name. And I've put that in there so we can see where the leaving group starts and then where the double bonds end up in the product. So a secondary alcohol treated in water as the solvent and a catalytic amount of strong acid, and then most likely some form of heat, leads to a dehydration. So dehydration is loss of water. So we have to lose the elements of H2O, and that is what forms the double bond. You'll notice the product manifold, there's 3 alkenes that are formed. And based on the numbering of the backbone from what we started with, you can see that those alkenes end up in different positions. So the question really is, if we're starting with a leaving group there, how do we end up with these products where the double bond kind of does not match where the leaving group was? So if we're using that as the alpha position, and knowing that we have to eliminate from a beta carbon, you'll see that some things have happened. So let's walk through stepwise what's going on here. So of the 3 alkene products, how are they classified in terms of their substitution pattern? So to recap how you solve that, you identify the sp2 hybridized carbons of the alkene, and then on each one you're just counting the carbon substituents. So this one has 1, 2, 3, and 4. So that will eliminate A and D. The second one, this carbon only has hydrogens, so we don't count those. This carbon has 1 and 2, so that's di-substituted. And then the last one, that carbon has H's there, so 2 H's. This has an H, so there's only one substituent, so that's mono-substituted. So for this one, we end up with B. And the reason we want to do that is those are the possible products. Can we figure out or guesstimate what's going to be the major versus the minor versus sort of trace products? Refresh your memory on what the structures are. So in general, what of those substitution patterns is the most stable? So the tetrasubstituted, so this one. So what would its name be then? So 2,3-dimethyl-2-butene. So of the three ones, which is the most stable? You need to. So with that, we would end up with C. So when you have to convert a name, or the name into a structure, really what you want to do is find the parent. So there's 4 carbons in the parent, and it says the alkene starts at position 2. And then from there, you want to add in the substituents. So at the 2 and the 3 positions are methyl groups. So that's how you want to move back and forth that way. So when 3,3-dimethyl-2-butanol is treated with acid, the blank will be protonated to generate and blank that will blank, resulting in the departure of blank. I heard a C, I heard an A, so it's between C and A. The difference is the nature of the intermediate that's formed. So we're starting with an acid. The alcohol lone pair is a base. So the alcohol is protonated. When that happens, that forms the first intermediate. Since the plus charge resides on oxygen, that's called an oxonium ion. That then ionizes, which means water leaves and you form a carbocation. So the answer for this one's A. So as we go through mechanisms, that verbal description helps us push the arrows of how the electrons move. So because oxygen's bearing the positive charge, that's called an oxonium. Now this bond is sufficiently weakened that it can ionize. So remember, ionize means you're forming ions. And we have to do that in a way to conserve the charges that are there. So this now is a good leaving group where water can be lost. So water is a nice small neutral molecule. That's an example of that entropy term that we mentioned a while ago, sort of increasing the chaos. So the plus charge that was on oxygen now goes on that carbon. Since we started with a secondary alcohol, that's going to generate a secondary carbocation. And you'll remember that in the carbocation stability trend, that's kind of the weird one where it's stable, but if it has the possibility to rearrange, it can. And so this is where we have to stop and ask some questions. So will this carbocation undergo a rearrangement, yes or no? And so the answer is yes, because otherwise we wouldn't be pursuing this line of reasoning. So when we use this nomenclature, alpha and beta, we really have to look at how many beta carbons there are and what can happen at each that will lead to the outcomes of a more stable carbocation. So this beta carbon here is a methyl group. So attached to it are 3 hydrogens. If a hydride shifts over, that will go from secondary to primary, and that's not favorable. This beta carbon has 1, 2, 3 methyl groups. So one of those methyl groups itself can shift over. So when that happens, what would the resultant structure be? So it would be C. And in blue, I'll write the numbering of the skeleton. So in our starting material, 1, 2, 3, 4, we see carbon 3 has 2 methyl groups. If one of them shifts over, now we can see that that carbon is left with 1, and then carbon 2 now has a methyl group. So that accounts for the skeletal rearrangement. So for the purposes of our class here, when you're looking at these beta carbons, the most common rearrangements are a 1,2 hydride or 1,2 methyl. It can get a little bit more complex than that, but these are the most common ones. The reason that it will rearrange is because what's the classification of the carbocation in choice C? So it's tertiary. So the secondary carbocation can rearrange to a tertiary carbocation. Once you do that, you kind of have to start over to answer the rest of the questions in the mechanism. So we were calling that carbon alpha. Since it rearranged, we're now going to call that carbon alpha and then reevaluate the beta carbons. So that whole group can move over. And then notice the charge just moves over in a 1-2 fashion as well. In terms of the numbering, the numbering that's listed is relative. So they're right next to each other, 1, 2. And the group that's moving is a methyl. So it's a 1-2 methyl shift. So at this point, we need to get out of the evaluation loop. Like when you're taking a shower and washing your hair and the shampoo bottle says lather, rinse, repeat, at some point you gotta stop, right? You can't keep repeating. So once we get to the most stable carbocation at that point, we're gonna stop and then move on to the next step. So now that's the alpha carbon. We need to evaluate the beta carbons for hydrogens to do the elimination. So how many beta carbons does this alpha carbon have? So we want the total number. So from here, we're just walking out. We see 1, 2, 3. 1, 2, 3 beta carbons. So how many total hydrogens are on those carbons? So we have 3, 3, and 1, so we get 7. Now the sort of crux of that issue is 2 of those beta carbons were the same. So these are the same. They have a total of 6 hydrogens. This has 1. So statistically, you'd expect an elimination to happen from something there's more of. But again, the product is determined by the stability of the resultant alkene. So from which carbon atom will a hydrogen be abstracted to form the most stable alkene? So it'll be C. So if we eliminated from A, and again, there's 6 of those type, you would get a di-substituted product. So there's always this balance of sort of statistically what you would expect versus the stability trend of the functional group in the product. So the outcome of this is you'll see more of the tetrasubstituted alkene produced, even though there's only 1 of those hydrogen atoms present. Bada bing, bada boom, that's E1. Doesn't get much different than that. The carbon skeleton changes, but that's pretty much it. Any questions? So remember, E2 is always going to have an oxygen base or an amine base. E1 is just going to be sort of solvent and heat. And then think back to SN2, SN1, what those conditions are. And then, develop a way of thinking about how you evaluate the reaction conditions to predict what's going to be the major product by what mechanism. So here's something to chew on, as they say. I call this putting it all together. So you've learned a lot of reactions so far. What can you do with them? How can we take cyclohexane and convert it into that allylic nitrile? Are there any choices we can eliminate sort of immediately? A little louder for the people in the front. You said D? We'll eliminate that, but let's take a step back. So A and C. So if you look at cyclohexane, it's a hydrocarbon. You only have CC and CH bonds. So you have to do a radical halogenation. And only chlorine and bromine are good for that. Fluorine is too much, iodine's not enough. So that really eliminates those two. You can't even get past step one. The nuance between B and D is just the order of how things are done. And so when you're trying to make something, you can have all the right reactions, but then you have to sequence them. So does anyone play chess? Let me ask this. Who knows the rules of chess? How each piece moves? Okay, so in chess, you have to know how the pieces move. That's important. But to play someone else, you have to sequence those moves to set them up so that you win. And that's really what this is about in terms of the logic. So we have to get something on there to do other stuff, because breaking a CC bond or a CH bond is hard, so that's why we activate it with radical halogenation. So the product of step one is chlorocyclohexane. There's only one unique set of H, so it doesn't matter which H gets substituted. The product of step two is an elimination. So we're treating with a base to do an E2. Step three is allylic bromination. So now we put in a bromine that can serve as a leaving group for step four, which is treatment with cyanide. So again, the individual reactions are important, but also thinking about how you can sequence them into making something more complex. That's really what synthetic organic chemistry is about. Any questions before we turn 90 degrees and start something new? So this all kind of builds on itself. Through the radical halogenation, we get a good leaving group. We can eliminate it to an alkene. And now we're going to look at reactions of alkenes through a mechanism called addition. Aside from acid-base reactions, which are just proton transfer, every other reaction has a nucleophile and an electrophile. So of these remaining reactions that we're learning this semester, the pi bond of the alkene is the nucleophile. It's supplying 2 electrons to react with an electrophile. So there's some common themes in the different addition reactions, but the nature of the electrophile will change. So when that changes, that allows us to make different functional groups. To start us off with this, our electrophile, I'm going to use this form A and B. And that's just going to represent the elements of the electrophile that add to the alkene. In this alkene shown here, I've labeled carbons 1 and 2 with those subscripts. So what makes these reactions a little bit complicated? If A and B are not the same element, they can get bonded to those carbon atoms differently. So going to the right, this is showing carbon 1 gets element A and carbon 2 gets element B. Alternatively, carbon 1 can get B and carbon 2 get A. And the term for that is called regiochemistry. Basically, who gets what. What further complicates these reactions aside from the regiochemistry? Remember that a pi bond consists of the cloud on top and bottom. So in addition to the orientation of A and B, is that electrophile coming from this face or the bottom face? Furthermore, how are these bonds being made? Are A and B adding at the same time? That's called synchronous. Or does A add and then sometime later B adds? So there's these issues of what face it's going to attack, the timing, and then ultimately what falls out of that are the stereochemical questions that have to be answered. So who gets what? And I guess one thing that I can say about this, these things where I haven't shown substituents, like these just bonds, these lines, that plays a role in determining how the electrophile adds to the alkene. to maybe put that in perspective, so here's two alkenes, and then attached to them are two different groups. One is O-methyl, and then the other one is a carbonyl in the form of an aldehyde. So really what you have to evaluate, how do these substituents affect the reactivity of that alkene? And that's through resonance. So you'll want to review how those attached atoms impact the electron density in the alkene. Probably one of the more harder concepts to understand, and I struggle with it to this day after 29 years of studying this, is stereospecificity. So the outcome of a reaction is products, and stereospecificity says that you can look at the products and tell what geometry, cis or trans, the starting material alkene was. That's related to the mechanism of how the things add to the alkene in terms of what phase and then the timing. So timing is another way of saying that is concertedness. Do the elements A and B add at the same time? That means it's a synchronous addition. Or does something add, some time passes, and then the other thing adds? That's asynchronous. In general, things that add in a synchronous fashion at the same time, that's called a syn addition. They add from the same face at the same time. Getting further down the engineering flow chart here, the alternative asynchronous, those can be syn or anti. So there's always this little asterisk with these things, and it's not clear cut. Anti-addition means one element added to the top face, the other one swung around and added to the bottom face. So that's an anti-addition. When we go through this, what I want you to keep in mind, how do you prove these things? What are the instrumental methods? The syn and the anti really relate back to NMR, specifically proton NMR and Newman projections. This is the menu, as it were, of some of the fine reactions we'll be sampling for the rest of the semester. So they have names. The names typically indicate what is happening and what product will be formed. The timing of the addition, whether a discrete carbocation is formed. So typically those are with the asynchronous reactions. Remember, if you form a carbocation, can it rearrange? You have to ask that question. And then the general stereospecificity. Can you predict what the geometry of the starting material was based on the product stereochemistry? So of all of these reactions, really what we're doing is making the functional groups that we learned in Module 1. And then you have to confirm that using the spectroscopic techniques from Module 2. In the prior lecture, when we talked about alkene stability, I mentioned that is measured by hydrogenation. And that's just the addition of H2 to an alkene. In this case, those elements A and B are equal, so they're both H. So there's really no debate on what carbon is getting what element because they're both getting hydrogen. So hydrogenation happens in a syn fashion. The H2 adds from one face of the alkene at the same time. So the model alkene that we're going to use for all of these is shown here, cis-3-methyl-2-pentene. I drew it this way, sort of with these bonds coming out towards you and that one going back, to give kind of a perspective of, how things can add from the top or the bottom face. So if you think of the alkene as sort of perpendicular to the projection, then you have this top face and a bottom face. So it occurs through a syn addition, and our product is an alkane. So hydrogenation uses H2 gas, typically with a precious metal, platinum or palladium, and then a polar protic solvent like methanol or ethanol. Just out of curiosity, has anyone run a hydrogenation reaction in their life? I've run a couple and they're kind of scary. The palladium metal is adsorbed onto essentially charcoal, so it looks like charcoal dust. When you add that to solvent and then you start bubbling hydrogen in there, if all of that is not in solution, then it will ignite and it will brown your underwear when it happens. It's pretty scary. So basically, you're bubbling this in, and at some point, if you're fancy about it and you have a regulator, you can measure how much hydrogen is taken up. But if you're cheap like I am, you just get a birthday balloon and put hydrogen in it and bubble it through. What's nice about this is you can also use deuterium gas, and then that will actually deuterium label those carbons, which increases your parent mass by +2. Any hydrogenation questions? So you've probably heard of partially hydrogenated vegetable oil. So these things are done industrially, and I'll have an example later on, maybe next week or the week after, about brominated vegetable oils. Have you heard of these things? BVOs. So how many of you like Gatorade or Powerade or whatever? So it's mainly water, but there's a color, right? So they used to put these brominated vegetable oils in there so that the color, which is a dye, is soluble in the water. So you chase these things by adding one chemical, you got to add another to make things homogeneous, and so on and so forth. So we're zipping along. All the lights are green on Hardy here. The next reaction is called hydration, and this is the opposite of dehydration. So we have now alkene, and we want to add the elements of water, H2O, across the pi bond. So this is our model. There's the alkene. So one carbon's got to get an H, the other's got to get an OH. So the question is, who gets what? These are the two possible products. You'll notice one of them is major, one of them is minor. And so why is that? This is known as Markovnikov's rule. When you look at the sp2 hybridized carbons of the alkene, you need to count the hydrogens on each. So that carbon 2 has 1 hydrogen. Carbon 3 has none. Under the conditions of hydration, which use an acid as the first step, the alkene's acting kind of like a base to abstract an acidic proton. So when it does that, it's going to form a carbocation. Markovnikov's rule basically says them as has gets. So carbon 2, since it has a hydrogen, gets a hydrogen, and that generates the most stable carbocation, which is then trapped by water. So verbally, hydration under those conditions will always produce the more substituted alcohol. So say you don't like substituted alcohols like that, don't worry, we'll learn another reaction that's complementary where you make the lesser substituted alcohols. Skip drawing that out because I've written it on other. Quickly want to hop back to this. So there's always two choices with these mechanisms that happen asynchronously about what carbon is getting the electrophilic reagent first. So if we show protonation of the green carbon, that generates a tertiary carbocation. If we protonate the blue one, that generates a secondary carbocation, and we know from the stability trend that's less stable. It takes more energy to form that, and so that's not going to lead to the major product. So a carbocation is a Lewis acid, which means it's an electron pair acceptor. The reactions are run in water. So the water is what will then trap that. So we're adding the elements of H2O, it's just not all at the same time. So the important thing, I guess, you know, I'm like every other American. I want everything right now. I don't want to wait. You do have to take your time and evaluate these routes so that you know what's going to go towards the major versus minor. You don't just want to start thinking, boom, it's going there, and then you're ignoring this other path because you might be missing some critical detail. So as you go through pushing the arrows, just take your time, evaluate it, sort of rank it according to some trend, and then more often than not, you'll arrive at the correct answer. Thumbs up, thumbs down. So let me slide. If you had an alkene and you wanted to determine the presence of the alcohol in the product, what method would best be used to determine that the OH group is there? So that's infrared because that has a nice broad OH stretch. In region 1. So try to remember what those OH stretches look like versus, say, a carboxylic acid. Now I think I want. Okay, so here is your decision point right there to draw out both intermediates, then evaluate them according to the stability. Since the tertiary is more stable, we have this carbocation. The water can trap from the top or the bottom face equally. So the result of that is a tertiary alcohol. So the difference between the secondary and tertiary, those are constitutional isomers of one another. Questions? So typically when you have an alkene with an acid, Markovnikov's rule is in play. The carbon with more hydrogens to begin with will get protonated because that generates the more stable carbocation. The next addition reaction is pretty much the same, but instead of adding water across the double bond, we're adding the elements of HX, where that is the form of some hydrohalic acid, HCl, HBr, etc. The thing I want to point out that's crucial to this the solvent is non-participating. It's just there to dissolve everything, to get the party started. What you'll notice is you do not see dichloromethane anywhere in the product. If the solvent is participating, that means you're going to see the elements of it in the product. So when you're on the exams and stuff, just make sure you're reading the conditions carefully so you can predict the right thing. So HBr, we can assign partial charges based on electronegativity. So we have an acidic proton. The alkene is always supplying the electrons. So it's going to do an acid-base reaction. Then Markovnikov's rule states that since that carbon has a hydrogen, it's going to get protonated. Just like in the hydration. So when it's protonated, we get the tertiary carbocation. That is then trapped by the Br minus. The Br minus is the nucleophile. That's the only thing that can trap that. The difference is when this solvent becomes participating, there's typically more of those around, and then it can trap the carbocation. So as before, this is going to generate the more substituted halide. One other note to point out, we've seen alkenes with HBr in the presence of peroxide. So that's a very subtle difference in the reaction conditions. An alkene, HBr, and peroxide will do something entirely different than this sort of addition. Essentially what happens is it's going to flip the product distribution where the lesser substituted halide is produced as the major product. So for the most part, all of these reactions have a complementary, partner where you can flip the product distribution. So as my kindergarten teacher, Miss Jurasevich, used to say way back in 1980-something, let's put our thinking caps on here. How many unique carbons does this molecule have? Anyone want to hazard a guess? It is not 6. You've fallen for the Jedi mind trick. So I'm showing the elements of HBr adding to that former alkene, and I retained this stereochemistry. And so that is the trick, the dirty trick, as it were. This is just an ethyl group, which is the same as that ethyl group. So the answer is 4. So it kind of looks like that has some stereochemical information, but it doesn't. So is that a chiral molecule? So the answer is no, because that carbon, these two ethyl groups are the same. Again, don't get fooled by, this little chem draw trick with the wedge there. What analytical method would be best to determine that there's a halogen in the molecule? So mass spec. This is a quick review. Melting point really doesn't tell you anything structurally. It might tell you something about purity if it's a tight range of like 1 to 2 degrees. Proton is your unique sets of proton, and IR is more of just functional groups present. So mass spec is good for determining the molecular formula, and then specifically halogens are useful for that. So this was the minor product. That is a secondary bromide. So is this a chiral molecule? Yes. So the answer for that's yes. So positions 2 and 3 are stereogenic. What are their CYP designations? So 2 is S. And then what do you think 3 is? So 3 ends up being S as well. So this is A. And if you've looked at this slide, you would have known that already. So what's the enantiomer of that compound? So if we have 2S, 3S, which one's the enantiomer? So 2R, 3R. So the enantiomers will have exact opposite CYP designations at each center. Any questions on HX additions? So the hydration in hydrohalic acid additions, those had electrophiles where the elements A and B were different. Halogenation is using X2, where X is typically chlorine or bromine. So each carbon is getting the same thing. So there's no issue of regiochemistry because they're both going to get the X atom. But there is an issue of stereochemistry because they do not add synchronously. So it's not a synchronous addition. So overall, from the face of the alkene, you get X adding from the top face, and then the other X adding to the bottom face. If we use bromine and dichloromethane, again, dichloromethane is non-participating. So CH2Cl2, you don't see that anywhere in the product. So it can't, it's inert, it doesn't add anywhere into the product. We're adding the elements of Br2 across that pi bond, and then what you see is one added from the top, the other added from the bottom. What you'll notice is this produces enantiomers. Because depending upon which carbon adds first to the top face, and then how the Br minus attacks from the bottom, you get that equally at the secondary and the tertiary positions. So we have achiral, bromine's achiral. Even though these have stereocenters, they have to be produced in a racemic mixture. You can't favor one over the other because nature will not allow that. Let me ask some questions and I'll go back and sort of draw more of the mechanism. If you conceptually think of a carbon-carbon pi bond, you know, that distance, then you think of bromine, it's a bigger atom, the larger van der Waals radii, so you have Br2. So, you know, say that the length of this pencil is the carbon-carbon double bond. And then Br2's like this, like big. You can't get both bromines adding at the same time because the distance is too big. So instead of the Br2 coming down like this, it just flips and adds this way, sort of like an axis. So you get one bromine adding first. When that bromine forms, it generates this thing called a bromonium ion. So what's the charge of the bromine? What? It has to be +1. So why is that? Because remember, you start with Br2, you're breaking a bromine-bromine bond. So the electrons in that bond have to go to the other bromine, and it ends up being Br minus. So you've added Br from one face. That face is now blocked. the bromide anion has to attack from the other face at a separate time. So that's asynchronous and then overall anti. The reason you end up with enantiomers that bromine has a choice of which carbon it's going to attack when it opens that three-membered ring. So if you took the product mixture in a sample cell and analyzed it by polarimetry, what would the optical sign of the optical rotation be? So this has to be 0. So you'll earn your money on this one. If you took that mixture and analyzed it by mass spec, what would the parent ion region look like? Considering that bromine has a natural abundance of 1:1 of 79 to 81 Br. Any educated guesses? What? So the answer is C. So with one bromine, the bromine can be either 79 or 81, but you have two of them in the molecule. So you have to think of the combinations, permutations, whatever, combinations of that. So really the way you get kind of triplet from that is looking at if both of them are 79 or both are 81, and then you have 79, 81, 81, 79. So that ratio is 1 to 2 to 1. And if you really want to get your brain in a twist, try thinking of it with maybe 2 bromines and 1 chlorine, 2 chlorines, 1 bromine. You get some really wild looking patterns because they have different natural abundances. I'm gonna cheap out, not show you the mechanism of that. Let's see, it's based on the time here. So just so we can get to these last couple questions. So that was X addition in a non-participating solvent. What if you have a nucleophilic solvent, so something that's protic? So either water or an alcohol. Now where there's competition where the solvent can trap the carbocation intermediate. So what you'll notice there, we're running this in chlorine and then water. and you see the presence of water in the product as OH, so the water becomes an alcohol. Chlorine is the electrophile. For the most part, it's going to form sort of the same intermediate, that halonium ion that's then trapped in an anti-fashion by the solvent. So you're adding X and then OH overall. We have the tertiary alcohol as the major, the secondary as the minor. So that should look a little weird to you. Kind of the rule of thumb is 2 arrows is fine, 3 arrows you're pushing it, and 4 arrows you're kind of in the psychological category of insanity. So we're bordering that, but at this point that forms a chloronium ion. So that intermediate can then be trapped by the solvent, which is then the nucleophile, and that's how you get the 2 different products. These things can kind of break open, and the way you evaluate it is you move the plus charge from the halogen to the carbon. You evaluate the carbon carbocation stability, and that's going to lead to the major product. So I think we have 2 more questions to get through in a minute and a half. So alcohol and halide chlorine, what techniques would you use for those? So IR for the alcohol, and then mass spec for the chlorine. So see if you can predict what the product of this will be. And then when you're done, you can just put your sheet up on the front. Please make sure you fill your bubbles.